Hey guys, Braz's Reptiles back again. So we're finally, I think after a year and a half of putting the first genetics video up, I went around to remaking the second one. I had them all made, put them on my Mac, and the Mac crashed. Completely crashed. I had to restore it, everything gone, and I just quite frankly haven't gotten around to doing it again. So I had the second one made, and it's going to be the tail end of this video. Just a little introduction here. Just wanted to let y'all know I'm still alive, still breathing, still kicking. We're still here. Little update. Let's see what's been happening. The banana male is I sent him to a friend's place up north. He's breeding a few of my females as well as a few of his up there, so that's exciting. The banana sulfur pen. And then what else? What else? What else? Oh, big news. So, actually, I didn't know the man before. I sent him up there. We've gotten to know each other pretty well, and we both went in on an inchy asphalt male. So, as some of you may know, the asphalt. Sorry, my computer's freezing. As some of you may know, the asphalt gene, whenever you throw it with a yellow belly, it's in that same complex, so you get a freeway. So that's pretty exciting. We have an inchy asphalt, which is, we need that inchy in there for that infamous Mardi Gras that Major League produced last year. So we're pairing that man up with probably, I think right now, about 6 or 7 females. He's pretty good size, so hopefully we'll get him around to a few more. But Okay, guys, back again finally with the second episode in our Ball Python Genetics 101 series. I know it has been forever, and I apologize. It's just been a long time. I actually made these videos. I probably made up to like the third or fourth one on my Mac, and my Mac crashed. So I had to restore it and lost everything on it. And this is actually my second try of doing this video tonight. The first time I recorded my screen with absolutely zero audio. So all you saw was my pen writing and moving, and not my voice. So that was great. So this is take 2. Excuse me. So let's get right into it, shall we? First I want to point out what my objective for this whole video is. After this video, I want you to be able to say, okay, I can walk away from this, draw up a very simple Punnett square, and figure out what by breeding X to Y what my statistics and odds are of producing what. You know, now I'm not going to prepare you to go cross a 5-banger to a 5-banger. That's a lot of work on a Punnett square. We're going to do like 1 gene to 1 gene, okay? So let's get right to that. So, okay, and this little software that I'm using has ads that pop up, so bear with me. Try to X out of them as fast as I can. Okay, so first thing, man, straight line. First thing we're going, holy cow, to breed is, I can't draw a straight line, is we're going to take a spider, and we're going to breed it to just a normal ball python. Nothing fancy about it, just a normal. So, like, a normal means we're going to go to Africa, we're going to pull a snake out of a hole, and it's going to be a normal. So another word for normal, sometimes you'll see, is wild caught. Okay, and spider. Spider is what we call a dominant gene. Okay, dominant genes, the only difference in dominant and codominant is with dominance there is no superform of the gene. Okay, so just keep that in mind. We'll get into that later. Okay, so what we're going to do is with a Punnett square is what you do is you set the genotypes of both the male and the female along right here. So for example, for this video's sake, we're going to put whatever picture right here, we're going to put its genetics right here. And then this picture right here, we're going to put its genetics here and here. Okay, so we're going to call a spider, we're going to just give it this little letter code for its genotype. I'm sorry, not, yep, NS. Okay, and our wild caught, we're just going to do 2 big N's. Oh, 2 big N's like for normal, or it doesn't matter. Just anything, just an arbitrary set of letters, whatever makes sense to you. I don't like the way I drew that S. Okay, That's not any better. So what we do with the Punnett square is we distribute these letters, okay? And again, this is a very basic Punnett square. A lot of geneticists would criticize how I'm doing this, but this is very crude and just to get a point across of what's happening and to help you better understand it. So it's going to be okay. So we're going to distribute that one to there, we're going to do that one there, and this one here. Okay, so we're going to put this in right here, like this, follow the arrow, we're going to put it there. This S, we're going to put it here. And then this end right here is going to follow the arrow and going to go here, and this end to there. Okay, so then what we do is we have to bring these letters down. So we're going to bring this letter down to here, and then we're going to keep bringing it down to here. Same thing here. We're going to bring this letter down to this box, and then we're going to keep bringing it to this box. Then we're going to do the exact same thing on these right here. We're going to bring this in right here. We're going to bring it over to this row. We're going to keep going into this box. And then this in right here, we're going to bring it to this one. Keep bringing it over to this one. Okay, so now that I confused you with a bunch of arrows, let's just do it. Erased my... Okay, so then we're going to bring this in. We'll bring these across first. It doesn't matter the order. That's irrelevant. So what I'm doing is I'm bringing this in over, and now I'm bringing this in over here. Okay, and now I'm going to bring this in. I'm going to bring it down. So we're going to put it here and here. And I'm going to take this S and I'm going to bring it down. Okay. So what we're doing now is let's just look and see what did we get whenever we bred a spider to a normal. What happened? Well, we see right here that, not big enough circle, right here that half of them, so 50% of the clutch are NN. Well, what does NN mean? We see over here that NN is the genotype for a wild-caught animal, or just a normal snake. So 50% are just normal. Nothing going on there, just normal snakes. Well, we see another 50% over here. Right here is NS. Well, NS we know right here coded for our spider, okay? So we know that 50% are normal and 50% are spiders. Okay, so just to recap. A dominant, and this is the same for a dominant or a codominant. A dominant to a normal gives you 50% normal and 50% of whatever that dominant or codominant gene was. Okay, so moving on. Let's get rid of the add. Okay, so now we're dealing with albinos. What is an albino? An albino is what we call a I don't like that. A recessive gene. What is a recessive gene? Great question. I can spell. Good gosh. Not even close. R-E-C-E-S-S-I-V-E. There we go. A recessive gene. What does that mean? A recessive gene just means that gene, in order for it to be visual and in a hatchling, it has to be on both the mother and the father's side of the clutch. Side of the the family tree, if you will. So the mom who laid that clutch has got to have either visual albino, she's either visual albino or het albino, and the father the same. He either has to be visual or het in order for you to have any chance at producing a visual albino. So we're going to get more into that, and hopefully it makes more sense. So a recessive gene, typically you code recessive genes with lowercase letters. So we're going to do 2 little a's. And then our normal or our wild caught, we're going to do the same thing. So we're going to do like we did before and break up these letters. And again, all you geneticists out there, I know this is rough, but we're just getting a point across. So let's bring our letters across. And I hope this didn't confuse you. I'm doing it at once. So what I did was I brought this in here, and then I brought the A down at the same time. But you get the same thing. So to me, everything looks the same. So we got 100% of something. But what in the world is NA? We see AA, we see NN, but I don't know about you, but I don't see an NA. Well, we have to understand what heterozygous, if I can spell, yep, that's right, and and homozygous means, okay? Whoa, got a little funky there. I'm still getting used to this little Wacom Wacom tablet. Okay, so heterozygous, what that means is it is not a visual animal. So in other words, this right here, this is a homozygous. It is visual, okay? I look at that animal, I see albino. I see a visual albino. So that is homozygous. Let's start with that one. Homozygous means that it has both of the genes present in order for it to make it visual. So, like for example, AA, that is homozygous because tomo means same. So two of the same small letters, lowercase letters. Heterozygous, hetero is different. So, like for example, if we took one of these letters N, we took one of these letters, right there, A. In A would be heterozygous because these letters are different. And one of them, that looks like a funky Q actually. In A, because this letter right here is a lowercase. Okay, so that means that it is part of a recessive gene. So this is a normal snake that is heterozygous for whatever A stands for. And in this case, it stands for our albino, okay? So we're looking down here in A. In A is heterozygous. So what that means is, we'll do het albino, 100% het albino. What that means is that every single animal in this clutch is going to look normal. They're going to look completely normal. They won't look albino. They won't look het albino. They just look normal. But you have to know that whenever you bred that albino to that animal, that everything in that clutch is het albino. You're not going to be able to look at it and see. So that's why keeping track and keeping accurate records of such things, that's really important, because you don't want to sell somebody an animal that's het for XYZ when actually it's not. So it really all comes down to record keeping and honesty, but as far as hets are concerned. But anyway, off topic there. So albino to normal, so a homozygous recessive to just a normal snake gives you 100%, like we saw right here, 100% heterozygous animals, het for short, heterozygous animals for whatever that recessive gene may be, and in this case, albino. So let's say, here, you know what, let's make a list of recessive genes. I feel like sometimes we get confused on what is what. So we'll do, whoa, just a second, let me get rid of that. Okay, recessive genes, okay. So what are some recessive genes? Man, I'm still getting used to this tablet. Give me some space here. I apologize. Recessive genes are, okay, obviously, let me write these. Let's write these in different colors, shall we? Albino, like we just did. Axanthic. How about clown? Genetic stripe. Oh my gosh, that's a funky G. Genetic stripe, we'll do GS. Lavender albino. Tri-stripe. What are some more? There are so many of them that it's just crazy. Just tons and tons. Hypo or ghost is a common one. There's a lot of them, but these are just a few of our very, very, very basic ones that you hear about most of the time. Tri-stripe, not really so much, but I like that gene a lot. So recessive genes, these are just a few examples. Albino, axanthic, clown, genetic stripe, lavender albino, tri-stripe, hypo. Those are just the few that come to mind right off the bat. But those are examples of recessive genes. Okay. So we just did, okay, here we go, yeah. So, what we're going to do is, I know this says normal, ignore that. This is a het albino snake. Ha. Okay, so we have a homozygous albino to a heterozygous albino. So what does that mean? That means that this animal right here is obviously, it does not look albino, but we know it's heterozygous or het
put a T there, heterozygous albino or het albino, which means that it carries that albino gene. So this animal right here has the ability or potential to make an albino. This animal right here obviously looks albino. It's an albino. It's a homozygous or visual albino. So we're going to give, let me write it in different. We're going to give it the code that we know we do for albino. And then this one right here, it's het albino. So we're going to give it that het code that we just learned about before. So let's break these up. So I'm just distributing these A's, and I'm going to put the big N here and the little a here. And I'm going to bring this N across, and bring this little a across, and I'm going to bring this a down. Okay, so what do we get? Right here, 50%, it looks like a 50-50 split, okay? Go away. 50-50 split of the clutch. 50% we see right here are NA, big N, little a. We know right here we saw big N, little a is codes for het albino, okay? And then, oh my gosh, what did I do? Okay, and then we see the other 50% are two small a's. We see two small a's are homozygous albino or visual albino. So you can produce, we'll do homo albino. You can produce a visual albino from an animal or two animals even that aren't albino, that don't visually look albino. They have to carry the albino gene, but they don't have to visually look albino. So that's just something to kind of keep in mind. So whenever we breed a visual or homozygous recessive to heterozygous for that same recessive gene, half of our clutch is going to be heterozygous for that recessive gene, and the other half is going to be homozygous or visual. So albino to het gives you 50% visual albinos. And again, that same theory applies for all of these and any other recessives that you can think of. Okay, so now we're going to breed a homozygous. Whoa. Let me get rid of it. I need to make my eraser bigger. There we go. Let's breed a homozygous albino to a homozygous albino. Okay, so we know right here that both of these actually are coded for two little a's. So let's distribute those. What do we get? 100% of oh, I don't like that green. I did the Punnett square in green. 100% of wow. Caleb, come on, that's rough. Of everything is two little a's. So, two little a's is homozygous albino. Homo albino. Homo for short for homozygous. So what that means is I breed a visual recessive to the same, wow, I don't know how that's doing that, to the same visual recessive, and every single animal in that clutch will be visual recessive. Okay? And same thing like before. The same thing we just did applies to all of these. This is for any recessive gene. Okay. So now we get a little tricky, okay? And again, geneticists who understand what we're doing, I know this is crude, but that's just how it is. Really, there's a lot more to this that we're just leaving out, just for understanding what we're doing sake. So, bear with me. Homozygous axanthic. Okay, so homozygous albino, two little a's. Axanthic, we're just going to call that two little x's, okay? So let's write those out. And this is a visual axanthic. Has 0 xanthophore. That's what axanthic does. And like albino takes out the melanin, axanthic, that gene takes out the xanthophore. So, let's look right here, and what do we get? Well, interesting. We get 100% of everything is some weird XA looking thing. I don't see XA on here. I don't know about you, but I don't. Okay, well, we know that in order for an animal to be homozygous or visual, that it has to have two, or homo, okay, because homo means same, so it has to have two of the same little letters. Well, none of these have the same, so that eliminates the possibility of any of them being homozygous. So none of these are visual albino or visual recessives. So what are they? Well, we know that the definition for het is different, okay? Different. So these are both different. You know, they're two different lowercase letters, X and A. So what that means is that they're what we call a double het. Double het means that they're het for both genes. Double meaning two. Double het. Het for the X gives it the het for axanthic and the A for albino. So we'd really call these double het snows because albino axanthics are snows. But we'll do double het albino axanthics. So a visual recessive to a different visual recessive gives you 100% of everything in the clutch to be recessive, het recessive for both genes. None of them will be visual, absolutely none. You will not get any albinos, and you will not get any axanthics. But 100% of everything will be het albino and het axanthic. So really, everything is going to look like this animal right here. They're going to look normal, but you just have to know that there are het for both axanthic and albino. Okay, so a spider to pastel. So spider is what we call a dominant gene, and pastel is a co-dominant gene. You don't really need to know that for this, but I mean you do, so you're not thinking it's recessive and dealing with it that way. But it doesn't matter that they're different as long as they're not recessive. That doesn't change anything. So we're going to code that with NS, and we're going to code this one with MP. So let's break that up. Okay, so what do we get? 25% is NN. Well, if we remember earlier, that is the same thing as a normal or wild caught snake. So spider to pastel, a quarter of the clutch is just normal. Nothing going on at all. Well, another 25% is NS. What we see right here, NS, is the same thing as spider. So 25% are spiders. Another 25% right here, NP. NP codes pastel. And then the last 25% is PS. Well, I don't see a P and I don't see an S, but together, but I do see a single P and a single S. So this little 25% right here is actually what we call a bumblebee. What is a bumblebee? A bumblebee is a visual spider and a visual pastel in the same animal. Okay, so that's what you're shooting for in this breeding. You breed a spider to a pastel, you want to produce a bumblebee. That's the nicest animal that you can produce. Okay, so breeding those two, a quarter or normal, a quarter or pastel, a quarter or spider, and a quarter or a mixture of both the pastel right here, and the spider. Okay, so dun 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 dun. Let's move on. You know what? We're gonna leave it on. That's fine. Okay, so NP, MP. So we have two pastels. Pastels is important right here. We have to know this when we're doing this. They are codominant. That means that there can be a superform of them. Superform is, we'll get into that in the next slide. It just means that it's basically like it doubled up upon itself. So let's see. What do we get whenever we breed a pastel to a pastel? We have to remember they're codominant. So let's break these up. NP to N and P. Let's bring them over in N, NP, NP, and PP. Well, interesting. We have our NN. Okay, we're good with that. We know what that is. Oh, percent. Bother me. We know what that NN is. We're good with that. We've got that. Wild caught. Okay. Well, and then we have, oh, we have 50% right here are NP. Well, we know NP is right here. We know that's just a pastel. So we're good with that one. But then we have this crazy PP thing. What is PP? Well, there's not a single P. Well, I see a single P. I see one right here and one right here. So what we call that is actually a super pastel, okay? And that's kind of something kind of hard to wrap your head around, but I'll get into that in the next one. So it's basically like pastel on top of pastel. So I'll get into that in the next slide, just so it'll make a little bit more sense. So remember, pastel to pastel. A quarter of the animals are normal, nothing going on there. Half of them are pastel, so half of them are going to look like their parents. And then a quarter of them are going to be that what you're shooting for in that breeding, which is a super pastel, okay? So actually, here's a picture of a super pastel. Say that like super washed out animal, like that's pretty awesome. Okay, so super pastel, like we just did before, we're gonna code it with two P's, two big P's, okay? To a normal, which we code for two N's. So let's break this up, okay? And see what we get. Well, we get 100% of every, golly, get kind of crazy there. 100% of everything is the same thing. It's an N and a P. Well, looking back at the previous slide, we know N and P is pastel. So, we breed a super pastel. We breed a super pastel to just a normal. This normal does not have pastel, does not have anything in it. It's normal. We get 100% pastels. So what basically happens is this pastel, whenever you breed a super pastel to anything, you know that every single animal in that clutch is going to have the pastel gene. It has to. The super pastel has to donate a pastel every time. So as we saw right here, it donated its pastel, not a super pastel. You won't produce a super pastel from a super pastel to normal, but you will produce pastels. So we produced every single animal as just a pastel. So that's we get interesting when we get into this. So a super form of anything. So let's list a few codoms. Super form of anything. It has to be codominant or there is no super form. So like pastel and fire and inchy and sulfur is like fire. Mojave, lesser, I don't even know. There are so many of them. Just crazy how many there are. But you have supers of all of these you're able to have a super form of, and that's because they're codominant. So basically you can double them on top of each other, and you get a super, orange drain. That's a lovely animal. You get a super form of that animal. So like a super form of a Mojave just so happens to be a blue-eyed leucistic. Same thing right here. Super form of a lesser happens to be a blue-eyed leucistic. Actually, same thing here with the fire and the sulfur. They're the same thing, except it's a black-eyed leucistic. An inchy, we just call that a super inchy. It's like it looks like an inchy on top of itself. I mean, it's like a much more attractive inchy. Same thing with the pastel. So that's just something to keep in mind with those. Okay, but now we get even more interesting. We're going to breed a super pastel to a pastel. Okay? So let's do that. Okay, what do we get? 50-50 split again. Well, this top 50 is NP, okay? We're good with that. 50% pastel, okay? Well, the bottom half, PP, well, we see right there that PP is super pastel. So here we got a super pastel. But that was because we bred that super pastel, we bred it to a pastel. So we were able, this pastel, half of the time, it donated its pastel gene, like we saw right here, it gave that pastel. And every single time, this has to donate a pastel as well. So it donated its pastel, and so did it. So a pastel on top of a pastel gives you a super pastel. So, just something to think about there. So, pretty interesting, guys. I think that's probably the last. I think it is. Yeah, that's the last of these slides. I apologize if there was some background noise this whole time. We had a room full of just crazy, rambunctious, sugar-filled kids next door. So that's what that was. Little siblings are just a joy. So guys, I hope that this helped you. I hope that I didn't confuse you more. That was definitely not the goal of this video. It was to help you better understand and grasp what's going on and what's happening whenever you punch into World of Ball Pythons, what you're breeding, you know. Oh, that's another great thing. And if you're ever doing something, go to, it's a different color, go to World of Ball Pythons.com and then click on their wizard tab. And that is an awesome little thing. It's like a Punnett square for you. It just does it for you. You can punch in what you're breeding, male and female, and it'll pop out your statistics and odds of what you're going to produce. So that's an awesome thing. Definitely for beginners and even advanced people. I mean, from every range of the industry, that's a great tool to utilize. But so I'm going to quit talking so this video isn't 2 hours long and get right to it. So guys, I appreciate you watching, and thanks for hanging around for this next video a year and a half later. I appreciate all the comments. You know, where's the next one? Where's the next one? It's here. It's back. I'm back. We're going to get to rolling with this thing, and it's going to be great. So, thanks for watching. Don't forget to subscribe and check back for episode 3. Thanks, guys, and y'all are the bomb.